Hi everyone, my name is José Luis Méndez Montezoca, and I'm a postdoctoral researcher in the Institute of Physics and Mathematics in Morelia, Michoacán, Mexico, at the Universidad Michoacana de San Nicolás de Hidalgo. And this is my contribution to the 32nd International Materials Research Congress, which is called Thermal Detection of Phase Transition of Pluronic F127 AQUEOUS solutions using thermal wave resonant cavity technique and mathematical models. And well, the aim of this work is to observe the phase transition of the pluronic hydrogels using the thermal diffusivity as a parameter of observation, of characterization. And well, hydrogels in general are materials which can absorb a high amount of water. And in the particular case of pluronics, these gels have a transition from liquid to gel state when the temperature is increased. Well, in the case of pluronics, to understand better this phenomenon, it is needed to observe the molecular structure of the pluronics. Well, the pluronics materials, pluronics are copolymer materials that have a polypropylene oxide block in between of two polyethylene oxide blocks. And the polypropylene oxide block is hydrophobic, and the polyethylene oxide blocks are hydrophilic. And well, in general, these molecules are hydrophilic, and it can be in solution in water if the concentration is low and if the temperature is low. But if the concentration is increased, it starts to form micelles as a structure of low energy, because this affinity of hydrophilic, hydrophobic, and another again hydrophilic. And if the temperature is increased, the polyethylene oxide block turns less hydrophilic, so some of the monomers that are in the solution start to organize also in micelles. So the number of micelles in the system increased, and it starts to packing and starts to entangle the corona of the micelles. And when this occurs, the system becomes a gel. So the aim of this work is to observe this transition using the thermal diffusivity. For this reason, we use the thermal resonant cavity technique, which consists in sending a sinusoidal signal from a locking amplifier to a laser driver to generate light source with a frequency, with a well-defined frequency. And this electromagnetic wave, this electromagnetic radiation is sending to a silicon wafer, which acts as a thermal generator. And so it converts the, the radiation into differences of temperature. And the silicon wafer can be immersed, well, is immersed in the liquid sample, which is located in here, in a chamber. And the silicon wafer is attached to a cylinder, which can be move it up or down using a stepper motor. And so this is equivalent to have different thickness of the material. At the bottom of the liquid sample chamber, there is a piezoelectric sensor with which we can obtain the signal of with the information of the temperature changes in the material. And usually this signal obtained is low in amplitude and have some noise, so it is pre-amplified and sending again to the locking amplifier. And the locking amplifier make a operation between the measured signal and the reference signal, obtained a clean signal with a well-defined amplitude and phase. And well, in this case, the phase is the difference in phase between the measured signal and the original generated signal, reference signal. And well, we use the heat equation, which says that if there is a change in the temperature in some point of the material or in some boundary, these changes are transported across the material in time and in space across the material. And how efficient is this transport is given by this parameter alpha, which is the thermal diffusivity. And we can solve this equation in one dimension. Well, to be able of use this equation in just one dimension, is needed that all this array of the light source, the silicon wafer, the sample, and the piezoelectric sensor are well aligned, so that the movement is in one dimension. And well, using this simplification, and the solution becomes quite simple. We used also another simplification, another consideration, which is called the thermal-thick approximation. It consists in considering the thickness of the sample higher than 2 times this parameter mu, which is the square root of the thermal diffusivity over P over the frequency used in the laser driver. And under these approximations, the solution becomes simple and is an exponential function, and we can relate the solution of the heat equation with the signal obtained in the locking amplifier, and we can solve for the imaginary part and the real part of this equation. And from the imaginary part, it is straightforward. We obtain a linear equation, and from the real part, we can linearize the equation using the logarithm of the amplitude obtained, R. And from the slopes of these lines, it is possible to obtain the thermal diffusivity of the material because it's inside the parameter mu. So using this equation where m is the slope of the curves, it is possible to obtain the thermal diffusivity. And this is a result of common experiments. Here we have the comparison between a sample with DI water, represented by the square, by the squares, and a sample with 20% of PLURONIC, represented by the circles. Well, in this case, the percentage is weight over volume, and The black color represents the signal phase, and the blue color represents the amplitude, or in this case, the logarithm of the amplitude. And it is observed a small change in the slopes between these samples. And this small change in the slopes is converted into differences in the thermal diffusivities. Here we have our prior results of the measurements on the thermal diffusivity of pluronics. Here we have two different concentrations. The triangles represent the 20% concentration of pluronic in the water, and the circles represent 18% of pluronic concentration in the water. And it is observed that if the concentration increased, the thermal diffusivity decreased, and this is because the thermal diffusivity of the polymeric material, in this case pluronic, is lower than the thermal diffusivity of DI water. And it is observed that before the transition, as the temperature increases, the thermal diffusivity of the liquid, in this case liquid, also increases, quite similar to the behavior of another liquids as water or alcohol. But after the transition, when the material is gel, as the temperature increases, the thermal diffusivity decreases. We regard that this unexpected behavior is because as the temperature is increased, the entanglement between the polymeric chains is also increased, and the thermal transport across the material is decreased. And well, to obtain this kind of experiments, we use also temperature control in the thermal wave resonant cavity technique to be able to have measurements with different temperatures. And we conduct an experiment to see if the signal, voltage signal in the lacking amplifier is affected by the transition, if one can observe the transition just observing the voltage. And this is a hysteresis cycle. The circles represent the process in which the sample was heating, and the triangles represent the process of cooling. This was just a ramp in a short time for this experiment, and we observed the transition during heating. Indeed, it was observed a change in the slope of the voltage. But during cooling, there is no transition. It was not observed. And we regard that this is because once the polymeric chains are entangled, is difficult to untangle even when the temperature is decreased. And we obtained a similar behavior observing the signal phase. Very similar to that observed with amplitude. And well, these are our prior results. As conclusions, well, we observed that this technique was able to detect differences in the concentration of pluronic, was also able to detect differences upon temperature in the thermal diffusivity. And it was possible also to observe the transition from this point of view of the thermal diffusivity. and we regard that this is another way to observe. Usually these materials are, this transition is observed with the viscosity of the material or with calorimetry also, but this is another way to observe the transition. And we hope that these kind of investigations give more information about the self-assembly of the polymer and about the transition itself. And well, as a future research, we are currently conducting more experiments with more concentrations, and we are looking for mathematical models to have a better understanding of this phenomenon from this point of view. And well, in future, it will be also important experiments with complexes, for example, PLURONIC with particles, as in nanoliquids or in medicine. And well, I thank you for your attention of this work. If you have some comments or questions, you can write here in the web platform of the Congress, or you can send me an email, and I will be happy to know about your comments. And I really thank you for your attention.